Okay, welcome everyone to 130B Quantum Mechanics. So today we are going to continue our discussion of quantum dynamics and hopefully finish that, and we will start part 2. Sorry for that. Last time, this Wednesday, I couldn't come, but I guess the TA has already covered the parts of Schrodinger equations and give you examples of how that works. But maybe let me briefly review that in quantum mechanics, states are described by state vectors, by these cat vectors. And time evolution, the Schrodinger picture basically saying that under time evolution, the state will evolve with respect to time, and the operator will remain unchanged. And the state evolve following the Schrodinger equation, which is generated by a Hamiltonian. And this Hamiltonian generates a unitary transformation to the state. By unitary transformation, you can think that is like rotating the state in the Hilbert space. So another way of viewing this dynamics is to consider the Heisenberg picture. So in the Schrodinger picture, because the state is depending on time, and the operator doesn't depend on time, which is a steady matrix, but the expectation value, because it has to do with the state vector operator as a matrix and that cat vector scalar product, right? So the whole thing will have a time dependent. So that's why certain observables will evolve with respect to time. But there's an alternative picture in quantum mechanics, which is called Heisenberg picture. Well, in this picture, the state remains in the initial state. So if you, at time equals t equals 0, whatever that state is, so the state will remain that initial state. What is changing is actually the observable operator that is evolving in time. These two pictures are equivalent because either you can think that the state is evolving in time by a unitary transformation acting on the state, which is an operator anyway, or you can think that you can absorb this unitary transformation to the observables, because in that way you predict the same kind of observable time evolution. So what we can really measure in experiment is neither the state nor this matrix that correspond to the observable, but the expectation value of the observable. When you perform experiment, you are looking for the average expectation value. So what is really evolving in time is this expectation value. But this expectation value, you can either think that the unitary actually acts on the state, so state has a time dependent, or you can think that the unitary is actually U dagger OU. It's like a conjugate transformation. It transforms the operator as a matrix. Previously, we learned that if you have a matrix, then the unitary transformation need to act from both sides, with U on one side and U dagger on the other side. So that's the operator transformation. So Schrodinger equation tells you, give us a differential equation that describes how the states evolve in time. Heisenberg equation basically is another equation of motion, which is still a time derivative differential equation, which tells us how the operator should evolve in time. So how this O as a function of t should be. So that's what we want to learn today. And then I should emphasize that one should only apply one picture at a time. So either you use the state, or either the operator is time dependent, but not both of them. So you need to, that's something need to be taken care of. So if you switch to the Heisenberg picture, if we choose that picture, then the time evolution of an operator is given formally by this unitary transformation, but it's also described by a differential equation, which is the Heisenberg equation. The Heisenberg equation says that operator as a matrix, if you want to take its time derivative, it equals to a new matrix, where the new to the right-hand side. The right-hand side matrix is just the operator's matrix at this time, and its commutator with the Hamiltonian, and then that gives you the operator time evolution. And then the derivation of this equation, you can take a look at exercise 25. But I think the basic idea is that previously, when we derived the Schrodinger equation, we basically take the infinitesimal time evolution. We consider this t to be very small, and then we can expand this u as a Taylor series. We know that this unitary is always generated by the Hamiltonian. So if you expand this u out, basically, it's generated by Hamiltonian. You will get something related to Hamiltonian, and after some organization, you can show that the commutator automatically appears, and then with that, moving terms around, you can basically derive the Heisenberg equation. I think the derivation is straightforward as long as we consider the infinitesimal time evolution. Okay, so that's what I want to say about the Heisenberg equation. But why do we need to switch to this picture? Well, there's some convenience because, for example, we have been talking about quantum mechanics all within this framework of state is a vector. But in classical mechanics, we don't talk about state. We directly talk about how observable evolve in time, right? For example, we talk about if a particle has a coordinate, and then under the action of a force, for example, how does this particle, how does this mass accelerate? And then how does, what's the time derivative of the coordinate, and what's the time derivative of momentum, right? So we care about how physical quantities like coordinate or momentum, or these observables, what's their time evolution dynamics? We care about their time derivative. So this Heisenberg equation allows us to make direct connection to those classical pictures. You can insert, for example, position operator. I haven't mentioned that yet, but maybe we'll talk about that today. If you insert position and momentum operator into this equation and use your Hamiltonian as your whatever classical mechanical system you like, there's a Hamiltonian governing that. So if you quantize everything and then put it into the quantum mechanics framework, you can pretty much recover all the classical equation of motion from this by this manner. So this equation, the only difference between these two equations is this is on the operator level, which is saying that this O as a matrix, the whole matrix of this operator is evolving. This is saying that if you evaluate this matrix on an initial state, so the initial state psi is given, so if you substitute a specific initial state, and then you take the inner product of both the left-hand side and the right-hand side with of this operator with the initial state, then become this equation. The reason that you don't need to worry about inner product with this initial state is because initial state doesn't depend on time, so there's no time dependent of initial state, then the time derivative only acts on the operator. That's why this equation leads to this one as a consequence. But this equation, which directly describes how observable expectation value evolve in time, is pretty useful because then you only need to compute this commutator and figure out how each operator commute with Hamiltonian into some other operator, and then you can write down the equation of motion. So that's why we will have a homework 6 in order to provide you an opportunity to exercise this Heisenberg picture, which can be useful. So the Hamiltonian, I think you have seen this Hamiltonian last time in the Rabi oscillation case. We will set h bar to 1, and then Hamiltonian basically contains two terms, and then one is sigma x, sigma z, and with coefficient in the front. So last time we will use this Hamiltonian to evolve the state vector and then compute what should be the expectation value of x, y, z on the new states, right? So, so this homework 6 is about trying to redo the same thing using Heisenberg picture and try to derive how in the Heisenberg picture where the state no longer evolve in time, instead the operator sigma, which has three components, sigma x, sigma y, sigma z, each one of them, I should say, each one of them is a 2x2 matrix. So, so the whole thing is actually, these are matrices, and then you are saying that the time derivative of each one of them equals to, this is like a super matrix, which combine this matrix. For example, partial t of sigma x equals to minus delta times sigma y. Partial t of sigma y equals, okay, there's a factor 2. 2 delta sigma x minus omega sigma z. So those are the equations you try, you need to derive in this homework. And the way to derive it is, I think it's not difficult. You just need to calculate all these commutators following the rules of Pauli matrices. And you can do that on algebraic level. You don't need to multiply this 2x2 matrix from time to time. I think that's not difficult. And with that, this is basically the Heisenberg equation in this system. And then you can take expectation value for each of these observables. Then you can obtain a similar equation which describes how observable expectation value evolve in time. But now, if I tell you that the observable expectation value is like 0, 0, 1 as an initial condition at the beginning, then basically by solving this time evolution equation, you can try to find how this, do you know how to solve it? You can use Mathematica D-solve. You can try to look at its documentation or search online, how do I solve differential equation with Mathematica. I think it's not a big problem that Mathematica will directly tell you the answer. And then with that answer, you can substitute this answer into this probability distribution and see it really still recovers the Rabi oscillation physics, which means that this probability is trying to compute what's the probability that you start from the initial state 0 and then end up with the final state 1. What's the probability for that transition to happen? And you will see that transition will happen in an oscillational manner. That's the probability will increase and decrease and increase and decrease, and so on, like that. Okay, so that's about homework 6. And okay, any questions? If not, then we basically finished part 1. So let me briefly summarize. In part 1, we have learned that quantum states are described by vectors, and then any observables are described by Hermitian matrices. Any time evolution is described by unitary matrices. Unitary matrices are always generated by Hermitian matrix. And then if you want to make measurements during the measurement of an observable, which is a Hermitian matrix, you only see those measurement value to be the eigenvalue of this Hermitian matrix, which are all real. And then after the measurement, if you confirm that certain outcome has been observed, then the system will collapse to a new state correspond to the eigenstate of this eigenvalue of your observable. Okay, so those are the basic principles of quantum mechanics and very general frameworks. So, but since we have been talking so far, we have almost only focused on like two-level systems, qubits, and discrete systems. We're talking about matrices. But previously, when we learned quantum mechanics, we know there's also concept of wave functions, like position and momentum operator, like you need to take derivative of wave function in space. So where does those come from? How does those ideas compatible with the matrix pictures that we are describing so far? So that's why I want to continue the second part, which is algebraic method, which is trying to tell you why we have been saying that states are vectors, but previously we know that states are also wave functions. Why wave functions? Are these two just different descriptions, or they are actually the same? Okay. So the first point I want to make is that functions are vectors. I think in the first part, we say everything are vectors. Everything is vector. So wave functions are also vectors. Let's see how we can view a function which seems so different from vector also as a vector. There's something that is in common because both functions and vectors are mappings. They belong to the general scope of the math. In math, basically, they map things from one domain to another domain. What a function does is maps the input to the output. It takes an input and then does some processing and then returns the output, right? That's what a function is supposed to do. For example, if we talk about a complex function defined on a real domain, what does that mean? That it's a mapping from a real number to a complex number. So this function, by saying it's defined in the real domain, meaning that it takes arguments, it takes the input, which belongs to a real number, and then it returns the output, which belongs to a complex number. So that's why for every real number within the real domain, it maps to a complex number in the complex domain, denoted as a psi as a function of x, right? So that's an example of a function. So now we talk about, actually that's an example of wave function. So a wave function of a particle in a one-dimensional line is exactly a function like that, a complex function defined on a real domain. Now a vector is also a mapping because it maps, instead of a real number, it maps indices to values. Because vector is basically an array of numbers, And this array of numbers are labeled by their indices, the first one, the second one, and so on. So once you tell me which one you want to know, then you are giving me an input of index. Then I look up this vector, look up this array of numbers, and then I extract the values for you. So that's also a mapping. It's like looking up a table. So for example, a complex vector is basically mapping an integer which belongs to the domain Z. That's an integer domain to a complex number. So all we are saying about complex vector is really a mapping from indices which belongs to integer to the values which belongs to a complex number. So by this analog, you can see that the function and the vector has pretty much the same structure. The only difference is that their defining domain is different. One is in real, one is in integer. But if you have a very long vector, then the integers will be very, very dense, right? So that almost approximates real numbers. So you can say if I run every one of my real number can also be run to integers. So there's no big fundamental difference between these two. So by this analogy, every function can be viewed as a vector with a continuous index. We just need to, instead of the index is discrete, we can think of this real number or the position of the particle in the wave function as a continuous index of the wave vector. So then a quantum state will, in terms of a state vector, if we are describing everything in terms of vector, the quantum state can be described, if it is described by a vector, then we call it a state vector, and then the state will be written as a linear superposition of the basis vectors with these components, right? The vector components as a coefficient in the front. And the statistical interpretation of this, amplitude or the component in the front is basically the probability to observe this the basis state I given the original state psi, or the other way around, I think. And then this probability is given by this wave function or state vector amplitude square, basically. So if it is a function, then we basically have a similar formula. You can write the abstract notion of the state as you are taking the wave function, and then there's also a basis state according to this, basically in correspondent to every position x. So this cat x, you should think of it as an abstract state, just like that basis state. What does that basis state mean? That basis state means that the system is in the I state. So this x means that the particle is at the x position. So the position labeled by a real number x. So this cat x state basically describes a state where a particle is at a definite position. And then in general, if the particle is actually described by a wave function, then that quantum particle is in such a state that's a superposition of the particle being in every different kind of position weighted by its wave function. And this wave function squared, again, give you the statistical meaning, which means that if you already know that the system is in such a state described by this wave function, then the probability to find this particle really at the position x is actually given by the wave function norm square. So given that, you can see everything is consistent with what we have learned so far in previous quantum mechanics courses, right? So that's why what we have been talking about so far, like matrices and vectors, are fully consistent with the idea of wave functions. Any questions? Hopefully that's clear, right? Okay, so previously when we talk about operators, we have been talking about identity operators and chronic delta symbol. So that kind of notion also need to be generalized to a new delta symbol, which is compatible with the fact that now the indices are not discrete but continuous. So for continuous index, people define the Dirac delta function, which is kind of like a continuum limit of a chronic delta symbol. It's defined by the following property under integration. So the delta function, if you multiply on any function and then integrate over x, that simply pick out the value of this function at the position x, basically. So by shifting the variables, because you can always shift x by x minus x prime, and then doing that integral doesn't matter. So basically, you can show that shifting these variables, you can have another equation. And this equation, why do I want to write this? This is like the definition of delta function, but this is a consequence of the definition. But that consequence basically tells us the behavior is very similar to what we learned about the chronic delta symbol. Because for the chronic delta symbol, it depends on two indices, I and j. And then if you are summing one of the index with a vector, then basically what happens is that you remove the summation and the delta symbol together, but replacing the I index by j index. That's the result. So it's the same idea for delta function. Delta function in this form also depends on two variables. One is x, the other is x prime. It's like I and j. Now, if you have any function, which is like a vector component, and then if you're summing over their common variables, which is like summing over the common indices, but instead of sum, you have to integrate because these are continuous variables, then the resulting function it basically gives by the other index or the other variable, okay? So essentially, delta function can be viewed, another way of viewing it more intuitively is like the unit impulse. Because the only function that has this behavior is like a very sharp peak, because you want to go to this, if you go to this integration, the reason that it extract the value of f at x equals 0 because delta of x it represents a peak at x equals 0. So if it is only a peak, meaning that it's only non-zero at x equals 0, then everywhere else when x is not equal to 0, it just doesn't contribute to the integration, right? And near x equals 0, it basically gives you the function value. And the reason that it gives you the function value is this impulse, although it's a very sharp peak, but the area below the peak is defined to be 1. As the peak becomes sharper, it also becomes higher. So you can think of it as a kind of a limit, for example, of Gaussian. So here is a way to understand that. This is called a Gaussian function. The Gaussian function basically describes a peak, and then there's a parameter called sigma, which is the standard deviation that you can change. So if you have a large sigma, then the Gaussian function will be very broad. But if you have a smaller sigma, then it will be very sharp, very peak very high. And then, it is adjusted in such a way that the area under this peak is always the same. No matter you have a larger sigma where it becomes broader, but it also becomes shorter. But if you have a smaller sigma, it becomes narrower, but it also becomes higher. So the area, which is the width times the height, is always the same under this curve. So in the limit that this peak becomes sharper and sharper, in that limit, that's the picture of delta, Dirac delta function. You should always think that it's like a very narrow and very high Gaussian function, but if you integrate over this function, it looks like it basically gives you integration. The area under the curve is basically 1. Okay, so loosely speaking, this delta function looks as if it's 0 everywhere, but only infinity at x equals 0. But x equals 0, this infinity is actually ill-defined because if I just say it's infinity, I couldn't infer that the area under the curve remains unity. So actually what need to also be defined is that this integration is 1. So given these properties, you can see delta function simply, if you multiply delta function on any other function, it basically suppresses the value of the function on everywhere else and only pick up the value of the function at position 0 under the integration. Okay, so that's the rule. So why do I want to talk about that? Because delta function is very much like identity operator. You can think of this integration as an operator acting on a state, acting on a wave function. And delta function has this nice property that it preserves whatever function that you give it, basically you get the same function out. Okay? So that corresponds to an identity operator in the continuum's limit. So with this mathematical preparation, I think we can start talking about position and momentum, which are concepts only defined for continuous variable quantum mechanics. So these continuous variables are variables whose eigenvalues can take continuous real value. Previously, we say that all these all these observables are described by Hermitian matrices, Hermitian operators. For a finite dimensional Hermitian matrix, if you diagonalize the matrix and then find the eigenvalue, the number of eigenvalue basically equals to the number of dimensions of this matrix, how many rows and how many columns, right? So a continual variable basically means it's a huge Hermitian matrix. The matrix has infinite dimensions. So it has infinite number of eigenvalues, and these eigenvalues are so dense that it forms a continuum spectrum, and then it's a continual real values. So in this case, it's very difficult to write down this infinite dimensional matrix, so people become more abstract. And instead of keep thinking of it as a matrix, we just define it on the operator level. So this is the eigenequation, for example, for the position operator. A position x of a quantum particle is defined by the position operator, and then there's a position eigenstate, where the position operator x on the position eigenstate gives you the position eigenvalue and use that value to rescale the eigenstate. So this x with a hat denotes the position operator, which is a Hermitian operator, correspond to the position observable of the particle. And this x without the hat is a number, which is a real number that corresponds to the position eigenvalue, which labels the position of the particle. And this x with a cat, basically in the cat vector, is the corresponding position eigenstates that correspond to the particle sitting at that position x. Okay? So the Hilbert space in this case is infinite dimension. Actually, it's continuously infinite dimension because the number of states there is infinite, and then it's labeled by a continuous number. And it's always helpful to think about this continuum eigenspectrum as certain limit of an infinitely dense discrete spectrum. You can always think that you are trying to define the position of the particle on a larger and larger lattice. Suppose the particle can only live on 1, 0, 1, 2, 3 on integer positions, and then if the lattice is very large, then looking at it from far, then the particle is almost like moving continuously in the space. So that's why you have many, many position eigenvalues, but fundamentally everything's still discrete. And this is actually a deep idea, whether our universe, the space and time that we experience every day, whether that's continuous or discrete. That's also a question under debate, because maybe from our everyday experience, we will say time and space are continuous, but we know that it's inconsistent with quantum gravity, because if you try to probe the smaller and smaller structure of space, then you will have to use higher and higher, you will have to use photons of shorter and shorter wavelengths, because in order to probe that very small structure, then you need your wavelength of your light to be comparable to that structure, right? And photon of very high, of very short wavelengths will have very high energy. And photon of very high energy will also have very large mass, because energy is also equal to mass, E equals mc squared. And then particles with very large mass will create a lot of gravity. And then the photon, if it has a very short wavelength and then very large mass, you are putting a lot of mass in a very small space. Then at one point, you will reach to a limit that this mass is so massive that it creates a strong gravitational field and collapses the photon into a black hole. So the photon can never come back. So you are trying to probe some small structure in the space, wishing to discover that the space is actually continuous. So you are using more and more high energy photon, higher and higher energy photon. Eventually, at one day, you send the photon there, and then it doesn't come back because it becomes a black hole. So that's the point. You stop probing more finer structure of the space. And that's the point where the space starts to look like discrete. And because of this, you can see in this argument, we use two facts. One is that the wavelength of the photon has to do with its energy, right? That's quantum mechanics. And the other is that if the mass of the photon is large enough, it can create a black hole that's gravitational, that's like a general relativity. So if you combine gravity and quantum mechanics together, you will have to believe that somehow there's a fundamental limit that we can probe the continuity of our space. So So some people believe, some physicists believe, our space is actually fundamentally discrete. And all this continuous space-time notion is just humans' illusion. It's not real. Okay, so that's just one kind of philosophy, but that doesn't matter too much. I just want to tell you. Here is a summary of the formulas that we have on the discrete side and on the continuous side. I think you can understand all of them quite easily if you just think of continuous quantum mechanics as a limit of discrete. So for example, we can talk about orthonormal basis, and then now the orthonormal basis will be labeled by this position, and particles of different positions will be orthogonal to each other. I mean, its quantum state is orthogonal, because if the particle is in position x, it's definitely not in x prime. So there are two distinct realities, right? We know distinct reality will be described by orthogonal states. And then you can also try to normalize the state. And then the normalization previously is 1, but here it becomes a delta function. And then resolution of identity, you just need to replace every summation by integration and replace every discrete index by the continuous index, and everything will remain the same. And then, for example, you can also decompose the state, and then you can define the scalar product, and then you can have these normalization conditions, and you can also define the scalar product between two states. Here, I want to emphasize that becomes the scalar product between two wave functions. So in continuous quantum mechanics, states are described by wave functions, and this is for the cat state, there's a wave function. For the bra state, there's a corresponding wave function, which is just phi star, which just complex conjugate. And then if you want to compute the scalar product, previously we know we need to multiply these vector components together. Now you multiply the wave functions together, and then summing over the indices, and then you're summing over the position, basically. So this is how you compute scalar product. Okay, so with all these analog, we can quickly move on to position operators. Position operator as a Hermitian operator, it also has an eigen spectral decomposition. Basically, every Hermitian operator, you can try to find its eigenstate and its eigenvalue, and use this eigenstate, eigenvalue to reconstruct the position operator. So I'm summing over all the eigenstates labeled by eigenvalue x, and then I put the eigenvalue x in between these projection operators, and then integrating it over x that defines the position operator in a very abstract manner. It doesn't tell you anything more, but it's just another way of writing it. Okay, so the reason I want to do that is because, again, wave function description is spaces dependent. For example, if you have a state, you can either describe it using a real space wave function, meaning that you represent the state in the position basis. You can also define it in a momentum space wave function. There's another thing like that. We will talk about that very soon. And then you can use momentum eigenbasis. So you can use different eigenbases to describe the same state. So wave function is a basis-dependent object. But if you write a wave function in this manner and define the state is basis independent, because you already specify what's your basis choice when you write down this expression. So this expression already becomes independent of the basis choice. And then applying a position operator on a state, you can basically use this definition. This is also a basis-independent definition of the position operator. And then when you apply on the state, what happens is you give you a new state where the new state has a different wave function. The wave function looks like the x as a number multiplying on psi of x. The reason is that when you're applying the position operator on these eigenstates, right, what happens is that the eigenstate gets rescaled by x. So that rescaling factor basically goes to the front and becomes this new wave function. So that's why we say that when you apply position operator on the wave function just simply gets multiplied by x. So the reason is that the reason is here, basically. So that's why sometimes people also loosely write position operator hump equal, which means it depends on your basis choice. If you choose to represent position operator in the position basis, then position operator really is not an operator, it becomes a number. It just becomes x multiplying on everything. So if you have a function of position operator, you can also define operator function. Like in quantum mechanics, sometimes we want to know what's the potential function. Potential function is a function of position, basically. So when potential function as an observable acting or operator acting on the wave function, what happens is that you just need to multiply this potential function v of x on this psi of x. I guess that's what you have already seen previously in quantum mechanics. So having talked about position, actually, any questions? Yeah.
If we go back to question number 16, could you explain again how we get into a binary operator is to having all in the integral? I don't see how we're getting there.
Okay, so equation 16, x is defined by this integral. Equation 16 is about applying this operator on this state. By definition, this operator is dx, x, x, x. And then this state, by definition, is dx prime, psi of x prime, x prime. Why do I need to use the x prime here? Didn't I just write x? But that's not a big problem, right? I can replace all these x variable by a new variable in order to not to collide with the existing variable that I have here, because I now have two integrations. So they need to have two integration variables. So now I need to integrate over x and x prime. But now this part and this part, you can smash them together. That becomes x, and then psi of x prime, and then x prime. So in this expression, this is a number. This is actually a real number. This is a complex number, but anyway, still a number. All the number can be pulled out because these are ket vector, bra vector, and ket vector. These vectors will have non-trivial scalar product, but the number doesn't matter, right? So you can pull out all the numbers, but don't pull it out all the way out of the integration because these numbers still depends on x and x prime. So you are not allowed to take them out of the integration. But within the integration, things simplify to this one. Now you have to use a formula there. What's the scalar product of the position basis? Position itself forms an orthonormal basis. So its scalar product, just like this orthonormal condition, it's a delta function. So it basically gives you dx prime, x and psi of x prime, and then delta x minus x prime. But for this delta function, we can do this integration very easily because you can eliminate delta function with x prime integration. But the only price you need to pay is to replace every x prime by x. Oh, I missed x here, actually. So that's the derivation. That's how formally you can arrive at the result. And then this derivation basically tells you that if you start from a state whose wave function is like this, and then you're acting on the state with a position operator, which looks very abstract. But in the end, what happened is nothing happened, but only the state wave function gets modified by multiplying an x. Okay? Yeah, so that's the derivation. Sorry for people online. Maybe I will take a picture of the blackboard and then post it later.
Sorry, Professor. Yeah. Are you using delta function characteristic, right? From the last step to the final one?
Yeah.
So get rid of the dx prime. To get rid of that differential, what are you doing?
So you get rid of x prime integration.
Okay. And that's one. The integral about that point is only exists an x and I get rid of everything else.
Yeah. That's the definition. The definition of delta function is such that delta function x minus x prime with any fx prime integral of dx prime equals f of x. That's the definition of delta function. Because delta function is a peak, and then this basically describes a peak at x prime equals x position. Then, of course, there's a impulse there. Then that impulse will pick up this function at that value, right, at that position. and then suppress any other positions. Okay. Okay, so this is about position operator. Any further questions? And with position, another thing I want to introduce is momentum operator. But before introducing momentum operator, I want to talk about translation, because momentum operator is actually introduced by translation. So with the preparation of position operator, I think translation operator is easy to understand. This cat x state is an eigenstate of position operator, which labels that the particle is at a certain position. So what do we mean by translation? Translation means you want to move the particle to a new position, and then that process is called translation. So when the translation as an operator acts on the state, it basically take the state to a new state, meaning that it moves the particle from x to x plus a, so that the particle is rest at a different position. Okay, and then this is called the translation operator. Translate every it actually acts on every x eigenstate, and then uniformly translate everything by the amount of a. So this translation operator is labeled by the amount of translation it's going to do. And then this amount of translation is denoted as a here, which is also a real number. So after applying the translation operator, the particle gets a new, end up with a new state at a new position. Therefore, this operator basically translates the particle by the displacement a. So in terms of the position basis, the translation operator can be expressed as this one, because this is the way that we write down operator. We say this basis operator means that you go and target this state, x, and then return a new state, which is x plus a. So for translation operator, what it needs to do is exactly go and target every position and then shift it by a, right? So this is the expression that corresponds to translation operator. And then you can show that the translation operator, because it corresponds to a basis change, implements a basis transformation. It basically shifts every x to x plus a. And this transformation is also, previously we say every basis transformation is unitary. And this particular translation is also a unitary operation. If you don't believe, you can try to check that this translation, you can check the t dagger t equals tt dagger. How do I perform a dagger on this operator? Then I just need to replace cat by bra by cat, right? I need to flip them around, so it becomes bra x and then cat x plus a. That will be t dagger. And then using all these rules, using this, in particular this rule, the inner product of the this x operator, sorry, this inner product of the eigenbasis of x operator, it forms an orthonormal basis. So using those rules, you can simplify these equations, and then you can show that it really corresponds to identity operator. And that's exercise 2. Okay, so with this definition of translation operator, we can talk about momentum operator. Translation operator is a unitary operator. What we have learned so far is that every unitary operator has a Hermitian generator. And then the Hermitian generator that corresponds to the translation operator is momentum. It's defined to be momentum operator. Previously, the Hermitian generator of time evolution is defined to be the Hamiltonian, which is actually the energy operator. And then the Hermitian generator of translation is defined to be the momentum. So momentum is whatever operator that you can put on the exponent once you exponentiate momentum operator, and then you can construct the translation operator as a unitary operator. So whatever Hermitian operator that needs to be put here, people will just call it momentum operator. So because of this momentum operator defined in this way, then you can show that you can try to extract what should be the momentum operator. Previously, we know that if you have this Hermitian operator, you can generate unitary. But if you know the unitary operator, you can also reconstruct the Hermitian operator by taking the derivative of the unitary operator with respect to its amount of translation, for example, here. So you just need to take t of a and then take this derivative and take a goes to 0. Previously, we have discussed this equation. I think I have explained why this equation precisely will give you the Hermitian generator. If you forgot, you can take a look at previous lecture notes. And then by saying that, this partial derivative basically means that you will take the translation operator that translate by amount of a, and then take the translation that translate by amount of 0, and then divide it by the amount of translation a and take the limits. So this translation operator should be thought as an infinite dimensional matrix. This is also an infinite dimensional matrix. So the result is still an infinite dimensional matrix. So that's basically momentum operator. But these are still very abstract. We want to know how momentum operator defined in this way really acts on the state. So suppose, so that's very important. We want to know the effect of momentum operator on wave functions, then we start from a wave function. Start from a state described by a wave function psi of x. So now under the translation, what happens is that under the translation operator acts on this state. It doesn't touch this coefficient. It directly go to target this basis vector, and then it translates x basis vector to x plus a to a new position. But now, because everything is within the integration, so you can redefine your integration variable by redefining a new x, which corresponds to ox basically minus a, for example. So you can replace this x plus a by an x, but then you have to replace this x by x minus a within the wave function. So this is what the translation operator will do to the wave function. So now if you apply this principle, now since P, the momentum operator is defined to be this limit that you have two translation operator acting on the state, and then you want to take their difference and then divide it by the amount of translation you are making, and then take the limit that this amount of infinitesimal translation goes to 0. Then it's very obvious that if you apply T0, which is translated by nothing, then it's an identity operator acting on the state, so the state remains the same wave function. But if you really have a T non-trivial translation acts on the state wave function will change from psi of x to psi of x minus a. So now you are going to take the limit of these two functions, because that's how you subtract two vectors with each other, and then by taking this limit, obviously, it becomes a derivative of this wave function with respect to x. So we can see what we have done so far is that if we start from a state which is described by a wave function psi of x, acting the momentum operator on the state actually does nothing but only modify the wave function. It modifies the wave function to a new function, where the new function is related to the previous function by a spatial derivative multiplied by some coefficient. Those coefficients are due to historical reason that people insist to put this IH bar in the front, but that's it. So there's a Planck constant. But essentially, what the momentum does is basically modify the wave function by a spatial derivative operator minus I partial x. Okay, so that's why people also often write momentum operator hump equal, meaning that it's basis dependent. So momentum operator can be represented as a derivative operator, really as an operator acting on the wave function. And then this derivative operator this is actually the position representation of the momentum operator, because this is how the momentum operator should act on the position basis state. Okay. More precisely, in the position basis state, there's a more involved equation where the momentum operator can also be written as this basis independent form, because this form, it depends on the basis choice. You are choosing the position basis. And then this form, it's not depending on the basis choice, because it already includes all your basis, specify all the basis. Is that understandable? If not, take a look at exercise 3. Exercise 3 is trying to show that if you define an operator looks like that and apply that operator on any state, eventually the state wave function will be modified by this differential operator as expected. So this is precisely the definition of momentum in its basis independent form. Yeah, if not, then maybe that's it for today. Thank you.